So this is where we move from the time domain to the frequency domain. Okay. And what we will do is give you a brief introduction to what we consider the frequency domain. When we say something in the frequency domain, we look at it and look at how to understand it. So basically we are looking at trying to understand what is the way of representing discrete time signals and systems in the frequency domain. So first and foremost, we are interested in the frequency domain representation. Okay, and what is the frequency domain? And so basically we are asking some very fundamental questions, and we will build it up from there. So here is what we have as the basis: frequency domain representation of discrete time signals and systems. This is our goal. But first, let us look at a very important aspect. Look at input signal which is given by x of n equal to e power j omega naught n. Okay? N goes from minus infinity to infinity. Basically, this is a periodic signal going from minus infinity to infinity. Output, when this is the input to any LTI system, the output will be given by, so if LTI system, output will be given by summation k going from minus infinity to infinity, h of k x of n minus k. Substitute for x of n. This is summation k equal to minus infinity to infinity, h of k e power j omega naught n minus k. Okay? And one more step, this is equal to e power j omega n, that is not doesn't depend on k, so you can bring it outside the summation, e power j omega naught n summation k equal to minus infinity to infinity, h of k e power minus j omega naught k. Okay. So what is the observation? Input is e power j omega naught n. Output is also e power j omega naught n, but it is scaled by a complex quantity. Okay. So this is the same as input. Same as input. Okay, and this is some gain which is a function of omega naught, e power j omega, call it as e power j omega naught, some function of e power j omega naught. And this is what is the starting point for our discussion, because what we see here is the input appears at the output with a scaling. Okay. Now, if you have a matrix A and you have a vector V, this comes out to, the output comes out to be lambda times V. This is called the eigenequation of a matrix. So, A is a matrix, V is a vector, and you get the output to be the same, but it's at a with a scale factor which is called the eigenvalue. So basically you say that V is an eigenvector of the matrix A. Okay, not eigenvector, eigenvalue. Now what we are saying is this exponentials e power j omega naught n are eigenfunctions. So e power j omega naught n, they are not eigenvalues, but they are eigenfunctions. And they are eigenfunctions not of one matrix or one system, they are eigenfunctions of all LTI systems. Okay. Now, if you want to know what is the gain of the that this particular sinusoid e power j omega naught is going to experience, then the only thing that you will ask is it an LTI system? then to tell me the impulse response. Once you give me the impulse response, I will compute this expression, summation k equal to minus infinity to infinity h of k e power minus j omega naught k. So this is what we call as the frequency response of the LTI system. Frequency response of the LTI system. LTI system, so therefore there is an underlying impulse response, that means h of k is present. For which frequency are we talking about? Omega naught. So basically it is a function of h and omega naught. So that is called the frequency response of a system. Okay, this is a remember the summation has got a complex exponential, so it will be complex valued. Now we can write this h e of j omega naught in the following form as some real part h r e of j omega naught plus j times h I e of j omega naught. Okay, now just for convenience, I am going to drop this omega naught. Basically, just call it omega. It is applicable for any value, not only for one frequency omega naught, it is valid for any omega. Okay, you have real part and imaginary part. Then you can also write it as the magnitude h e of j omega. This is a complex quantity, e power j times the argument of h e of j omega. Okay, so basically you can look at the frequency response of an LTI system in terms of the real part and imaginary part. You can also talk about a magnitude and phase component. All of them will depend on impulse response and omega, right? They're all dependent on those. So basically input-output relation. So you can talk about it in terms of the real and imaginary part, or you can talk about it in terms of the magnitude and phase part. Okay. So let us look at a couple of quick examples and see what this frequency response really looks like. So first is an example where y of n is equal to x of n minus n naught. Okay, it is the input delayed by n naught units of time. Okay, so I am going to ask you what the h of n is. Remember at the start of this session, we looked at such, this is basically a delay, not by 1 unit of delay, but n naught units of delay. No problem. This is the same as delta of n minus n naught. Remember, that is what, when you convolve x of n with delta of n minus n naught, you will get x of n minus n naught. That's what we have. So I want to compute the frequency response h e of j omega. This will be summation k equal to minus infinity to infinity h of k e power minus j omega k. That is from the definition that we had used, frequency response. But only one non-zero term is there, and that happens at n0. So basically this comes out to be e power minus j omega n0, the frequency response. Okay. So h e of j omega for this particular LTI system, which produces a delay of n naught units of time, is given by e power minus j omega n naught. Okay. Now tell me what is the magnitude of this. H e of j omega is equal to magnitude of a complex exponential e power j omega n naught. This is equal to 1 for all frequencies. Equal to 1 for all frequencies. So basically it is a constant value. Okay. What is the argument of h e of j omega? Okay, so basically you want to look at what is the e power j times what is the argument. So the argument of this the gain, the frequency response of this LTI system is given by minus omega n naught. Okay, the magnitude response is a constant. The frequency response, it varies linearly with omega. So this is what we call as linear phase. Okay. Delay is a LTI system which can be explained or described in the frequency, in terms of its frequency response, as a LTI system which has constant gain for all frequencies, and the phase changes linearly with frequency. So basically, so this is the starting point for our understanding and for our discussion that we are going to be developing and expanding. So here is the formal definition of the Fourier. We will call it the Fourier transform, discrete time Fourier transform. Discrete time Fourier transform. This is going to be the chapter of Fourier transform. This is going to be the topic of study for the next unit. And we're just going to introduce the basic, the concept and definitions. If I have a sequence x of n, and I'm going to be looking at it in terms of the Fourier transform, and this will give me xe of j omega, which is given by summation n equal to minus infinity to infinity, just like we did for the LTI system. This is going to be x of n e power minus j omega n. Now, x of n can be a sequence. It can be the impulse response. The impulse response also happens to be a discrete time sequence, so you can talk about. But if you are taking the Fourier transform of the impulse response, that will give you the characterization of the LTI system. Otherwise, it's the characterization of the sequence that we are talking about. Now, if you are doing the forward transformation, you must also be able to do the inverse transformation. Any transform, you must be able to also go in the backward direction. So, the inverse transformation, where given xe of j omega, you compute x of n, this is given by, we are going to show the proof of it in the next class. It's going to be 1 over 2 pi minus pi to pi xe of j omega e power j omega n d omega. Okay. Now, before we go very much further, I want you to at least feel comfortable that this is something that you have already seen. Now, you may say, well, no, we've never seen anything called discrete time Fourier transform, but in signals and systems, you would have studied what is called Fourier series representation of periodic signals, correct? You take a x of t, which is periodic, and then you compute the Fourier coefficients, and then write the sequence or the periodic signal as a Fourier series, which will be sum of the Fourier coefficients times the fundamental frequency and the harmonics. So actually, this is a counterpart of the Fourier series. Let me explain what I mean by that. X e of j omega. What is it a function of? It's a function of omega. And omega, we know from discrete time omega is always periodic with period equal to 2 pi. So, this is a periodic signal, correct? This is a periodic signal. A periodic signal with period equal to 2 pi. With period equal to 2 pi. Okay. Now, how did you compute Fourier series coefficients when you were computing Fourier series in the continuous time? You said 1 over period minus t by 2 to t by 2, basically the period. So, what is the period for us? 2 pi. So, 1 over 2 pi is nothing but 1 over the period. Minus pi to pi is over 1 period, you integrate the periodic function. What did you, this is the periodic function. Okay. What did you multiply it by? E power j. There in that case it will be omega times t and d omega. In this case it is omega n d omega. So, I hope you are comfortable to say that when I have a periodic signal, I can represent it in terms of the Fourier series coefficients. So you can think of this sequence as nothing but Fourier series coefficients. And once you have the Fourier series coefficients, this is not a the real valued Fourier series, is a complex valued. So you have Fourier exponents which are both positive and negative frequencies. So this periodic signal xe of j omega is given as a summation of some coefficients times the exponential. So that the forward transform, if you interpret it as a Fourier series, then the inverse transform comes out to be just the computation of the Fourier coefficients. Okay. So with this as the foundation, I hope that you will now start to feel comfortable that we can, given any discrete time sequence, we can go into the Fourier domain or the frequency domain, study it, analyze it, and look at how we can always come back to the time domain to recover the original signal. So this is the very important tool that we have developed. So we have understood all about discrete time sequences, discrete time systems, and now we are saying whether it's a discrete time sequence or a discrete time system, I will be able to combine it to form, to look at it in not only in the time domain but also in the frequency domain. So that is the next step that we would like to do. So we will stop here, encourage you to read sections. So this is covered in Oppenheim and Schaefer, section 2.6. Okay, section 2.6, that's the frequency domain representation, and we will build on this starting in the next session. Okay, so do look at all the examples that we tried out. If there are any questions, you can pose the questions to Mr. Tony, and we will explain them. I will also see if any concepts need to be reviewed or represented to you. That will also be helpful for us in terms of how to make sure that your foundations are very strong and that now we are able to move from time domain to the frequency domain. Thank you very much.